Hey everyone. Okay, so this week we're going to do a Propagation of Uncertainties lab, and this will involve simple harmonic motion. So it's a simple harmonic motion lab, right? Which is this is a simple pendulum. So we're going to be using a simple pendulum, and this is primarily for the purpose of introducing you to this concept of propagation of uncertainties. Okay, now first a bit about the simple pendulum. So a pendulum of length L, which is oscillating with this small angle theta. So here would be big angle, right? That's not what we're talking about. Small angle here, theta, say like 15 degrees or less, has a period that is determined by t. The period is 2 pi times root L, where L is the length of the pendulum, over g. Okay. Now, technically speaking, L is the distance between the pivot point there and the center of mass, right? So here, something like this has all of the masses pretty much down here, so the length of the pendulum would be the distance between this, my bottom hand and my top hand right now. Okay, so this is for, like I said, for small theta. You can look in the lab manual. There's the exact answer for larger theta is in there as well. But this is the one that we use for a small angle. It's a small angle approximation. And we're going to use a simple pendulum then, its length and its period, to then measure g, the free fall acceleration. So here you can see I've solved this formula up here. I've solved this formula up here for g. Now, when we make this measurement, we're going to measure the length of the pendulum many times, and we can get the uncertainty on the length of the pendulum by taking the standard deviation of our measurements of L divided by root n, where n is the number of data points or the number of measurements that we made. And we can do the same thing with the period t, right? The period t is going to be the standard deviation of those measurements that we made of t divided by root n. So we have uncertainties that we can get on L, the length of the pendulum, and t, the period of the pendulum. How do we then get the uncertainty on g? That's exactly what we're interested in for this lab. So let's first, before we get into the exact formula for the propagation of uncertainties and how we figure that out, let's just first talk about how to make a pendulum. So you're going to use phi-fox in this lab, and I can make a pendulum out of a phone so that I can use phi-fox on it very, very quickly. All I need are some rubber bands, some string. You can use dental floss, that would be perfectly fine, and a mask. Right, we all have like 150 of these at home, right? So just you can use a mask, and then lastly, your phone. So here's how I do it. I take my phone, I put it in my mask like this. Here's my mask, right? I set my phone in there. I can take rubber bands and strap it on. Okay, get it nice and tight. I would use multiple rubber bands and wrap them around a few times, but I'm trying to do this quick. And then I would take this string, and like I said, you can use dental floss. Right, just kind of wrap it around here. Okay, so I've tied the thing around both ends. Okay, now I can swing the thing back and forth, right? And what's nice about this is, see, it doesn't twist like back and forth like that. If you do that, the phi-fox measurements are not going to work well. That's not going to work out well. So what you want is something that can oscillate back and forth like this without having the face shift, back and forth. Okay, so I can take this, and I would put this somewhere. Right, I'll show you. I'll put it somewhere where I used it to make my measurements. Okay, just wanted to show you how not to do it. So here's an example of how not to do it. See how both of the strings are coming up to the same point there? Well, then when you go to oscillate it back and forth, it's just going to spin. Okay, and then it's not going to work out well with phi-fox. So don't do it this way. Do it the way that I have it, where the two are separated out, and then they go up together. There's a string that's wrapped around the pivot point, tied separately to each end. Okay, so now I've got my pendulum set up, right? There's a fixed pivot point there, right? Notice that there's a string is tied on this end. It goes over the pivot point down to this end here so that these two things are separate, right? They're not squished together like that. So now I can take this thing and I would go to Firefox, go to the results thing, set it up so that it runs for 10 seconds to get until it measures t with 3-second delay on it. And I would set the thing in, I would hit start, and then I would set the thing in motion. Okay, see how it's the face of the thing is always pointing in the same direction, so that's key. All right, now this is the way that I would measure my period t, okay? And I can take my meter stick here, right, and measure, make many measurements of L, the length of the pendulum. The important thing here is to measure, right, from the pivot point down to the center of mass, which is just where the center of your phone is. You're gonna have to make several measurements, okay? What I would do is suggest make a different starting point, a different reference point every time, or flip your meter stick upside down between making measurements, because you don't want to measure the exact same number every time. That's not a good measurement. If you're measuring carefully, then you'll get a little tiny difference between the different measurements that you have. Okay? Now, some of you might not have a meter stick. I'm sure many of you don't. You can use, so here's a little simple ruler that I would use, that I could also use, okay? If I had a longer pendulum than my measuring device, then I would just have to take a piece of paper and mark out different increments on the piece of paper using the measuring device, right? Say, okay, I got 5 inches here, and then mark my ending point, put it over here, okay, make another 5 inches, do that again to get the, if I have a 13-inch long pendulum, okay, and then convert from inches to meters. So you're going to have to improvise, though. You're going to have to figure out a way to make your measurements of L. And one last thing is, if this is not working for you, if your phone is dead, or I don't know, something, if Firefox is not working for you, you could just make a different pendulum. You could just make some kind of a pendulum if you want to, and then use the timer, say a stopwatch, to measure t. Just let the thing go through like 5 oscillations. Hit start, let it go through 5 oscillations, hit stop, then divide that number that you got by 5, right? That would be a decent measurement of the period. And then you could do that 10 times instead of using Firefox. But we prefer that you use Firefox in order to do this. All right, now let's talk about propagation of uncertainties. So, propagation of uncertainties is the way that you would, say, if you were measuring the volume of a cube, determine the uncertainty in that volume, the derived quantity, based upon the uncertainty that you have determined yourself on the length, the side length L. So, if you measure, say, the side length L of a cube, you can get the volume, right? You can get the volume from the length using V equals L to the 3rd power, right? V equals L cubed. Now, how would you get the uncertainty on V from the uncertainty on a measurement of the side length L? Now, that's a different story. That's a little more complicated. So let's talk about the procedure that we can use to determine this. So you know what a differential is, right? If you take, say, dy dx, that's the derivative of y with respect to x. Each one of these is a differential. So if you have, say, y equals x to the 3rd power, something, then you can do dy dx is equal to, well, that x to the 3rd would be then 3x squared. You can multiply dx on both sides, right? You would have dy equals 3x squared times dx. Okay, here would be, these are in terms of differentials then. So this would be the exact thing that you're going to do to get the using a differential in V and a differential in V, you can relate the uncertainties. So here's how that would look. A differential in V of V would be, well, it's the differential of L to the 3rd power. So that would be 3L squared dl. And Now, a small volume element is related then to a small length element, side length element this way. And you might notice, I mean, this is a small change in volume. This is a small change in length. Uncertainties are very similar, right? Uncertainties are small changes in some measurement, right? The only difference is that uncertainties, we even write them like this, right? Volume plus or minus some uncertainty in the volume. That plus or minus there is reflects that we don't know which way the measurement is. We don't know if it's biased high or biased low, right? We just know that there's some uncertainty. If we knew whether that was a positive or negative bias, we could just add it to the value and get a better value, right? But there's an inherent uncertainty about the sign. So what we do to derive uncertainties here at MSOE is to take plus or minus, say, a volume element. That can be substitute in an uncertainty in volume, and you could take a plus or minus length element dl, and that could substitute in the uncertainty in L from that. So the idea here is just with the signs is that both of these have our positive quantities on the right and left hand side. I can substitute in then the uncertainty in the volume over here and the uncertainty in the length over here. But even if there was a minus sign over here, something like that, I would still substitute in this uncertainty in V as the positive quantity, because that sign has an arbitrariness to it when we are talking about uncertainties. So let's just apply that then. So I can put in the uncertainty in the volume, and that would be 3L squared times the uncertainty in the length. Okay, great. Now, so this is in terms of absolute uncertainties. So in terms of relative uncertainties, so I would just divide both sides of this, say, by volume. If I divide both sides of this by volume, I'd have delta V over V is equal to 3L squared delta L over V. Okay, so on the left-hand side here, I have the relative uncertainty in the volume. If I plug in L to the third for this volume on the bottom here, then this would be equal to 3L squared delta L over L cubed. So I can cancel that and that out. And I would then have that the uncertainty on the volume is equal to 3 times the relative uncertainty in the length. So I have relative uncertainty in the volume is equal to 3 times the relative uncertainty on the length. So that would be my final answer. Note, this one here is perfectly correct, right? This is just a different form, and it looks a little nicer. Now, this should make some sense to you. The relative uncertainty on the volume is going to have some relationship to the relative uncertainty in the length. Certainly, if the relative uncertainty in the length is large, then the relative uncertainty in the volume is going to be larger, right? So it should make sense then that on the right-hand side of this equation, right, you need to multiply that uncertainty, that relative uncertainty, by a number greater than 1 to get the uncertainty in the volume on the left-hand side. Okay, so that's just one example. And this one is pretty simple because there's just one variable. V is a function of one variable there. Let's talk about one that's a little bit more complicated. Okay, so now let's do a little more complicated example. Let's talk about the volume of a cylinder. So the volume of a cylinder is defined in terms of 2 different variables, right? It has the length here, L, and R, the radius of the end cap, right? So the volume of a cylinder is pi r squared times L. What then is dV in this case? Well, here we have a function of multiple variables, and in the case where you need to get a differential of a function of many variables, say here I have a function A, a hypothetical function of x, y, z, and t,
could throw in any other variables you'd like as well. The differential will follow this form here. There is a partial derivative with respect to x times dx. There is a partial derivative with respect to y times dy. There's a partial derivative of a with respect to z times dz, and a partial derivative of a with respect to time times dt. Now, what is a partial derivative? Some of you are wondering. A partial derivative is where you take the derivative of a function. So here, let's just specifically talk about del a del x. So when you're doing the partial derivative of a with respect to x, essentially you're going to take the derivative with respect to x and you're just going to pretend that all other variables are constant. So let's just take some hypothetical function. Say a is x times y squared. Okay. When I take a normal derivative, dA dx, well then I have to do this whole product rule thing, right, where I take, if I call, say, this the first function and that the second one, I have to do the first times the derivative of the second. So the derivative of the second would be 2y times dy dx plus the second times the derivative of the first. So there's the second function. Derivative of the first would just be 1. So it would be this long thing. But the difference is when you take a partial derivative is you just pretend that the other values don't depend on x. So unless there's explicitly an x in there, y is not going to depend on x. So when y does not depend on x at all, then you can treat it like it's a constant. So when you take the partial derivative, I'm just going to pretend that y squared is constant in x. So it's just fixed. So I can pull it out front. So, and I can just take the partial derivative with respect to x, right? That's just y squared, right? So it was just that second term here of the two terms when we did the full derivative. So the moral of the story is that when you take del a del x, okay, this is a del. It's a funny looking d. That's a del. When you take del a del x, you're just basically going to say, I want to take the derivative d dx of the function a, where we consider y, z, and t are constants. We kind of pretend that a is constant, or that y, z, and t do not depend on x, right? So del a del x is a little bit different than dA dx in this way. Let's do then what would del a del y look like here? Del a del y would be, we have x times y squared. We're going to pretend that the x is constant with y. So we would just have this times derivative del y of y squared. Well, x times 2y then. Okay. So our differential of a then would be del a del x times dx plus del a del y times dy. Del a del x would be y squared dx plus del a del y times dy is going to be x times 2y times dy. Okay, now just to make sure that I'm not like making this all up, I could take this function, divide both sides by, say, dx, or dA dx would be equal to y squared plus 2xy dy dx. Okay, which was exactly what I got up here. So this is a legitimate way to do a differential, and these del's, when I say I'm pretending here that y and z and t are fixed when I'm taking the partial derivative with respect to x. I mean, I am pretending that those things are fixed, but which is not necessarily the case. But the thing is, there's other partial derivatives here that make up all of those other dependencies that I'm pretending are not there in this particular term here. So this is the way that you would do a differential. Okay, now let's go back to our volume element then. dv. It's going to be del v del r dr plus del v del L times dl. So that is del v del r. So it's just, I'm going to take the derivative of v, pretending that L is fixed. Okay, so pi L then times the derivative with respect to r of r squared is 2r. Okay, that times dr. Okay, plus now I have del v del L, and I'm going to pretend that r is fixed now. So that pi r squared thing gets, that's just a constant, and the derivative of L with respect to L is just 1. So that times dl. Okay. So there I have it. My volume element for a cylinder, 2 pi r L dr plus pi r squared dl. So I have my differential, my dv. Now let's put this in terms of move from differentials to uncertainties in the quantities. So this would transform then to delta v is 2 pi r L delta r plus pi r squared delta L. Cool. Now I'll get it in terms of fractional uncertainties, relative uncertainties, dividing both sides by the volume. And I can substitute in for v the pi r squared times L. Okay, notice that the pi r squareds cancel out here, and the pi's cancel out there, and the L's cancel out here, and the r in the numerator cancels out with the r squared in the denominator. So I have delta v over v is 2 times the relative uncertainty in r plus the relative uncertainty in L. Okay, now you might start to notice some patterns here, right? V up here in our first problem was L cubed, and we ended up with the relative uncertainty being 3 times the relative uncertainty in L. And here we had the volume was pi times r squared times L, and I had a single factor of the relative uncertainty in L and 2 factors of the relative uncertainty in R. So there is, this generalizes to a certain power rule. I'm not going to derive that for you, but there is an appendix to this lab that does exactly that. And so you can look at that in this lab and see that there's some rules there that are derived for you. But I think it's more important in this video to just show you the procedure, how you take and find these things. Very briefly, I do want to mention, because some of you who have, say, taken AP statistics or know your statistics really well know that this is not exactly the way that you learn it in a stats class. So in a stats class, actually what you would find is that this would look like, basically you would have delta v over v squared is equal to 2 delta r over r squared plus delta L over L squared. Each one of these terms would be squared in the relationship. The reason, so this must be technically the technically correct answer. The reason why we don't do this in physics is because one, it's very complicated to explain where these squareds come from, and we don't want to make this a class on statistics. We want to make this a class on physics, so we'll keep it simple. The other thing is that your uncertainties will be larger if you don't include these squares there, and that's good because we don't want to underestimate our uncertainties. That's when we end up excluding known values by quite a bit and things like that. It's better off for us to underestimate. It's better off for us to overestimate our uncertainties a little bit because we also usually don't quantify systematic uncertainties. We usually only quantify our statistical uncertainties. So we usually underestimate them as it is. If we use this version of the formula without the squareds, then at least it makes them a little bit bigger. Okay. With that, let's go to the one that we need for today's lab. So in today's lab, we're going to use this t equals 2 pi root L over G. Now, we're going to use t and L and their uncertainties to get G and its uncertainty. So let's first solve this for G. Square both sides. Can multiply by G, get that over here, and I'll divide by t squared. So then I have G is 4 pi squared L over t squared. Okay, so I have G is 4 pi squared L over t squared. Now, let's figure out how to get the uncertainty in G from the uncertainty in L and the uncertainty in t. Okay, well, the differential dg is going to be del G del L times dL plus del G times, or del G del T times dt. All right, so that would give me dg is, well, del G del L, I'm just going to pretend here that t is fixed. So I have a 4 pi squared over t squared would be constant, times the del L, just the L is left, dl. And of course this is just 1. Then the second term, del G del T. So here I'm going to pretend that L is fixed. So 4 pi squared L stays there. And do del T of 1 over t squared. And del T of 1 over t squared is just, well, this is the same as del T of t to the minus 2 power. So this would be minus 2 t to the minus 3. So I can substitute that in, 4 pi squared over t squared dl plus 4 pi squared L times this minus 2, do 1 over t to the third dt. Okay, now I can do my substitution. Now remember, the substitution was to go from plus or minus dg to delta g, and the same for plus or minus dt to delta t. Okay. What we want is, even though there is a minus sign here in front of dt, I want that to be a delta t, a positive delta t. All right, and of course the same thing goes for L. Okay, so let's do this transformation for this equation here. I would have delta G equals 4 pi squared over t squared delta L plus 4 pi squared L over t to the third. There's that minus 2 dt just be 2 delta t, right? Because the minus dt here also goes to just a positive delta t. Okay. Now, now that I have this, you guys remember the procedure. Put it in terms of relative uncertainties. So if I divide both sides of this equation by g, and I'll put in g is that 4 pi squared L over t squared. Okay, so I just substituted in g is 4 pi squared L over t squared. Now I can start to do some canceling. Well, 4 pi squared cancels out there and there. There's a t squared in the denominator and a 1 over t squared in the denominator, so those will cancel out. This just ends up being delta L over L. And on the second term, 4 pi squareds cancel out. The lengths cancel out. And in the denominator, I'm going to have a t to the third and a 1 over t squared. So that's just going to become a t in the denominator. Or in other words, I got delta L over L plus 2 delta t over t. So this is exactly how I'm going to get the uncertainties in G from the uncertainties in L and T. I'll get the uncertainty in L, say from the standard deviation of my, say, 10 measurements of L, and divide it by root n, where n is the number of measurements, so it would be root 10 if I took 10 measurements of L. I'll do the exact same thing to get the uncertainty in the period T, and I will plug those two numbers in there. I will also plug in the average L and the average T, and then I can determine G from the average L and the average T from this equation up here, and then I can use that to get my uncertainty in G using this equation here. And this is just called propagating uncertainties. We're going to propagate from our uncertainties in L and T, which we can measure directly, propagate those uncertainties to an uncertainty in the derived quantity, which is G. Okay, good luck in your experiments.